Okay, it's come to that time of year where we've finished the specialist maths course, and a lot of students ask me that when they get to the end of the course, they say, "Can you teach me complex numbers again because I've forgotten?" And the reason why that is because it's a standalone topic. We do it very early in the year. We often do it early, very early in the year in term one. So I figured that we would go and I'd make this video to go through as many complex numbers exam questions and concepts as I can. Can I just say that I'll go through a little bit of calculator, but to be honest, there's if you go menu 3.1, that will give you solve. And I think that the most important thing is if you stick a C in front, that is number one, C solve is the most important thing you'll ever need on your calculator. And the other one is a C factor. Okay, but for the most part, you can go ahead and you can convert to polar form and do all sorts of things, but in actual fact, you should be able to do a lot of that by hand. So I'm going to get started. When I get a chance to show you how to use a calculator, I will. Now it says here it says find the principal argument. Now the principal argument, the argument of z is we want to sort of find that angle. Okay, now a lot of students will actually do this in Cartesian form, and I think that that's wrong. Okay, the reason being is because it's so much easier in polar form. Now they'll do it because they algebraically they can do it, and yes, you can do it. You can go 1 minus root 3i over minus 1 plus I, and you can multiply it by its conjugate, which is minus 1 minus I over minus 1 minus I. Now, for the most part, that will work, and that'll be fine. But sometimes the algebra can be quite tricky. So I'm not going to show. I'm just going to show you what I think is the best way to do things. I'm not going to show you 3 or 4 different ways. I'm going to say whenever you have something like this, you convert to polar. Okay, so you convert to polar. Now, if you're converting to polar, what I'm going to do is, first of all, 1 minus root 3i, you should be instantly be able to know that the magnitude of that would be the square root of 1 squared plus minus 3 squared. That would be and also it's important for you to draw it 1 minus root 3i is going to be sort of 1 minus root 3. It's going to be in this quadrant here. Okay, and we've got some reference angle. Therefore, if I can say like tan theta is equal to y on x, basically that's what we're looking at. We're looking for the reference angle, and then we can go ahead and find it and apply what quadrant. So if I had tan theta is equal to root 3 over 1, then therefore theta is equal to, well, where is tan theta is equal to root 3? Well, if I think about sine of 30 is a half, sine of 60, so it's pi on 3. However, therefore, we can say that 1 minus root 3i applied in the fourth quadrant would be equal to the square root of 4, which is 2 cis of pi on, not pi on 3, it's going to be minus pi on 3, isn't it? Because this is on your formula sheet. Arg of z must be between pi and non-inclusive of negative pi. So we've got to go around this way. You can't go around this way because if you hit pi, you can't go any further. And that's a specialist maths thing. Okay, so we've found 1 minus root 3i, and we might as well find what 1 minus I is, but that's actually going to be quite nice and easy because 1 minus 1 plus I is going to be over here, and we know that that angle is going to be 45 degrees, so that's going to be pi on 4. So therefore, we could say that 1 minus 1 plus I is equal to, straight away, root 2 cis of, in the second quadrant, 3 pi on 4. Now, we've done all our side work. That's going to give us some method marks. So therefore, we can say that Z is equal to 2 cis of minus pi on 4 over root 2 cis of 3 pi on 4. Oh, actually, sorry. 1 minus root 3. What did I do that? That's minus pi on 3. Okay, 2 cis of minus pi on 3. Very easy to make silly mistakes like that. And I will make them. I'm not looking at any solutions here. I'm trying to do this as though I'm doing the exam and, well, trying to explain it at the same time. So that's going to give us 2 over root 2, and then that's going to give us cis, and there's going to be minus pi on 3 minus 3 pi on 4. Now we can just go straight and skip a step. We can go, that's going to give us minus 4 pi on 12 minus 3 pi on 12 minus 9 pi on 12, which is minus 13 pi on 12. Now the question is that the principal argument? Is that in this argument or this range over here? No, it's not. So the answer, therefore the answer, we'll put a little box around it, is equal to 2 over root 2, and there's no need to simplify that. Cis, we're going to add 2 pi to that. So we're going to add 24 pi on 12. So therefore your answer is going to be 2 on root 2 cis of 11 pi over 12, and that is your answer. Now, if I was doing without explaining it, probably would take around about 3 minutes. How are we looking at the moment? I've talked about quite a few things. Let's have a look at how long we've spent. So, okay, 7 minutes. But I certainly wouldn't be, you don't have to explain it in the exam. Now, that was an exam 1 question. Now, this is an exam 2 question. You might be sort of saying, I might want to get out my calculator. Well, you're wasting your time. Now, whenever you see anything such as this, and you've got to write this in Cartesian form, what you need to do is you need to go ahead and straight away, you need to go ahead, and we know that Z is equal to X plus YI. And then we're going to put that into this equation. We've got X plus YI minus I is equal to 1. Now, let's collect our real and imaginaries. We've got X plus, let's put a Y at the front because that's our imaginary part. And we've got Y minus 1. And let's do that to the square. Well, we'll do that, the magnitude is equal to 1. So therefore, we can say that the square root of, the magnitude of that is the square root of the real component squared plus the imaginary component squared. But that I is it's just the imaginary component. There's no I there, like so. So therefore, we now need to we square both sides. So therefore, we can say that x squared plus y minus 1 all squared is equal to 1. And we stop. We're done. That is our Cartesian equation. And as you notice, that is a circle. That is a circle centered 0, 1. Okay, didn't take us long either, did it? Don't need to pick up a calculator. Find the points of intersection of the graphs with rules z minus 1 equals I and z minus 1 equals 1 in Cartesian form. So we know that this was a circle. This one was a circle, center 0, 1. Okay. So let's find the Cartesian equation. In my opinion, that's what the best way to do it. And let's use our calculator. So once again, we've got x plus x minus 1 x plus yi minus 1, like so, is equal to 1. And then we've got x minus 1 plus yi, like so, is equal to 1, which will give us the square root of, let's collect them, x, we collect the real part squared, and the imaginary part squared is equal to 1. So therefore, we've got x minus 1 squared plus y squared is equal to 1. Now, of course, we now have that, we can call that equation 2, if you like, and we can call this equation 1, and we can say to find the point, so we can say the CAS, find the point of intersection. Well, we've got a circle. If really what we've got, you could draw it. We've got a circle which has a radius of 1 and is centered at 1, 0. So we've got 1 here, like so, and that's going to go to there, and that's going to go to there, and it's going to go like so. That's what it's going to look like. And then we've got a circle which is centered 0, 1, 0, 1, and it's going to go to there, and it's going to sort of go across like so, and so you can probably see where the intersections are without even getting your calculator out, but I wouldn't advise that. I would go straight to the calculator. So I'm going to pause it for a second and show. Okay, so I've just done a solve system of equations, menu, algebra, solve system of equations, and like so, and I'm just putting those equations in. Now, that's the thing, sometimes like you could probably have a bit of a guess as to where they're going to meet, but we know that, I can tell you now that they're going to meet at the origin. It's going to have 2 solutions, but let's see what the calculator says. That's where you are wasting your time if you're trying to do too much. Look at that, x equals 0 and y equals 0, and x equals 1 and y equals 1. So there's got to be some, find the points of intersection. There's got to be some method mark. So what we can say is that they intersect, it says find the points of intersection. They intersect at 0, 0, and 1, 1 is our answer mark there. Okay, so that coordinate there is 1, 1, and that coordinate there is 0, 0. Okay, so that's sort of an exam question. Now it says sketch and label the graphs. Well, look at that. We've got a nice we've got a circle here. We've got a circle that starts here. We can draw sort of roughly what they're going to look like. So we've got that, and as you can see, so you need to be able to identify. There's our one circle, and then we've got a circle which is going to sort of meet there at 1, 1, like so. There you go. Sketch and label the graphs. Okay, so this here is the graph of what are we talking about? This is z minus 1 is equal to 1, and this is z minus I is equal to 1. Okay, and you should be able to recognize those, that the moment I see the modulus of something is equal to a number, then you should be able to recognize that that's a circle. So once again, another 2 easy marks, and you can see there, that's where they intersect these 2 points. Find the equation of the straight line which passes through the points of intersection. Well, wouldn't you think that if I've got this point here, 1, 1, then that line here, okay, we've got a rise. We've got a rise of 1, and we've got a run of 1, and it goes through the origin. So isn't that just find the equation in a line which passes through them? Now, I believe it's only worth 1 mark. So wouldn't it make sense that that's going to be y is equal to mx plus c? Our intercept, it actually is going to go through there. So of course y is equal to mx. And of course the gradient would be 1, isn't it? Because it's 45 degrees or it rise over the run. So that's y is equal to x. That's all you need to do. You should be able to recognize that straight away. Now it says a straight line. The thing is with complex numbers is that, yes, it is a fairly easy topic, but some of the exam 2 questions can be pretty tricky, very tricky. And sometimes they can be very hard to interpret. So a straight line found in part D can be expressed in the form z is equal to a minus z bar. So alpha minus z or alpha z bar, where alpha is some complex number. Now be careful, the alpha is some complex number. Find the value of alpha. So the question is, we really have to sort of, this is the one that's really got to think, you've really got to think about it, because when we move on, part E is actually we've removed. And just so you know, whenever you've got these regions and intersections and things, these have actually sort of been removed from the course. Okay, so I've removed that one, and in actual fact, that wasn't the hard one anyway. This was the question which students really struggled with. So I want you to have a bit of a look at this question. Maybe even go back. I want you to have a bit of a think about it, because this one's the tricky one. Okay, so I'm going to pause this video now. I want you to have a little bit of a think about it and think about how can you possibly multiply. Now, first of all, you've got to go back to what Z was. What is Z? Okay, well, Z is, x plus yi. Okay, so let's say that x plus yi, and then we've got alpha, which is now z bar is x minus yi, isn't it? What could alpha be? I've given you a big hint there. So I'm going to stop this one, and I'll get how do you make those equal? Okay, so I hope you had a little bit of a think about it. Look, we've been told it says the straight line found in part D can be expressed in this form. That's the hint. So the straight line intersected its 2 points, 0, 0 and 0, 1 and 1, 1. We know 2 of those points. So what we can say then is, now 0, 0 is not going to be very helpful, because if we use that point, then it's not going to be very helpful at all. So why don't we substitute 1, 1 in? Which means we've got 1 plus I is equal to alpha, which we don't know, 1 minus I. Now, how do we actually go ahead and do that? Well, if we know that alpha is an element of our complex plane. So why don't I let's try some things. Alpha, it looks to me as though, why don't I do a little bit of a switcheroo? If I do I times minus I, that's going to give me minus I squared, which is equal to -1 times -1, which is +1. Okay, so that works. What about if I do I times 1? That's going to give me I. Notice there that is equal to 1 plus I. So therefore what we can say is if I have 1 plus I, that's equal to the same as if I had I times 1 minus I, like so. Or we could do it the long way. So you could do it by inspection, or we could say, okay, alpha is equal to 1 plus I over 1 minus I. Now we've got to multiply by the conjugate. 1 plus I is going to be 1 plus 2 I plus I squared. And then we're going to have a 1, and then we're going to have down the bottom we're going to have a minus I squared, which is plus 1. Now that's going to be equal to 1, I squared is negative 1. That's going to be 2I over 2 is equal to I. So therefore alpha is equal to I, and so you've got to save yourself some time by probably just sort of using a little bit of logic, or you could have actually just rearranged and rearranged to find alpha there. Okay, so that one was a bit of a tricky one. How did students go in that part D? I just wanted you to show you how students went in that, because that one was from 2011. So I'm going to pause this and whilst I go. Okay, so the first one where students are required to find the Cartesian equation, done very well, obviously. And of course, then they had to find the intersection of the 2 points using their calculator, basically. The question was very well done. Then drawing those two questions, or drawing those two circles, naturally very well done. But as you can see here, part DI, where it says that this one here, you can see there that 24% of students got 0, 41% of students got 1. So that was the separator question. That had less than 50% average. And in actual fact, the last part was a region between two circles, and that wasn't done very well. But some regions have been removed. Will they more ask you now to actually look at or drawing circles, lines on the complex plane? They will not ask you to find any regions anymore. So that actual question's done, and we've done the hardest part of the question anyway, as you can see. So it wasn't done very well. So they've just sort of said that A is equal to I. All right, and of course you would have had to have shown your working, and we've quite adequately shown our working there. Okay, so now just quickly, we've got this question here. It says factorize. If you want to have a go at this question, pause the video right now. Okay, so have a quick pause of the video if you want to right now, because I'm going to go through it in about 2 or 3 seconds. Okay, so I'm going to do this question without much explanation at all, and I'm going to show you how quickly you can do these things if you do it the right way. Now it says here f of minus 1. That means that z plus 1 is a linear factor. Okay. Now the thing is that you could, if that's a linear factor, what I'm going to say is, this is the way I would do it, then I would have z plus 1 times, and we know that we're going to have a z squared. And we know that we're going to have a 20. So I'm actually going to factorize this by inspection. Now it says here to factorize. Now, of course, this is a 2010 exam. So we need to do, we're going to find out what this value is in here. Now, if I go ahead and I go z times z squared is z cubed, that's fine. Z times 1 times 20 is going to give me 20. What about if I do 1 times z squared? 1 times z squared is going to be z squared, but then I'm going to have to do z squared, then I'm going to have to do alpha z times z. So in actual fact, I've got, therefore, alpha must be 8. So I've just factorized by inspection. A lot of you will waste your time and go ahead and waste your time and divide, and you do your polynomial division, and you'll do z cubed, blah, 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 divided by z plus 1. If you can factorize by inspection, do so. Now, if I'm letting that equal 0, actually, no, we're just simply factorising it. So if we're factorising it, then what we're going to do is we've got z plus 1, that's factorised. Now, can we factorise? Is there two numbers that multiply to give 20 now to give 8? There's not. So what we're going to do is we're going to complete the square. Z plus 4 all squared, okay, minus 16 plus 20, like so. So we can say that f of z is equal to that. We don't like wanting nothing equal to something. Now, the thing is that in the methods course, you're going to have z plus 4 all squared, and you've got this plus 4 here. Now, how can you possibly solve it? Well, on the complex plane, you can. You have SOPs, which is the sum of perfect squares. In other words, let's change, which we basically turn to dots, the difference of perfect squares, because that's z plus 4 all squared minus 4i squared. So therefore that's equal to, and now this is going to be our answer as well, z plus 1, and that's going to be, now let's do it, it's z plus 4 minus 2i, z plus 4 plus 2i, and we're done. Now, I bet you it wouldn't have taken that long. I reckon you could, if you were really on the game, you could do that in 2 minutes. Okay, so I'm going to just pause it now and just show you how students went in this question. Now, yes, students did do well in this question, but errors included in assuming both z plus 1 and z minus 1 were factors. Well, that's silly, because z plus 1 and z minus 1, they're not a conjugate pair. The conjugate pair is this thing. These two things are conjugate pairs. So you can see here that if you find those, when you find those and solve those, those come in conjugate pairs. We haven't been asked to solve that, okay? But what I'm saying is that was question 1. It was done very well, but the question is, how long did it take you to do it? Did you spend 6 minutes on it? Because I can tell you now that the students who want 30, 35 plus, they could have done that in 1.5 minutes. I can promise you, without explaining it, I could do it in a minute 20. Okay, so got to be mindful of that when you're doing your exams. How long are you taking? If you're taking too long for things, you're going to get flustered in an exam. If that should be your bread and butter. So if you get a question like that in your factorizing, solving, completing the square, you should be nailing that in exam 1 and not taking long. Okay, now I've just got a question here, which is from an exam 2 and it's worth 3 marks. Let me just see if it's, for some reason I seem to be missing. No, I've just taken part of a question. Now it says here z equals 1 plus I. Now this is why I talk about polar form as well, because if z is equal to 1 plus I, that's equal to root 2 cis of pi on 4. Now the power of that is that if I go z squared, then if I do root 2, then that's going to be root 2 squared, which is going to be 2 cis, and I'm multiplying the angle by 2, which is de Moivre's theorem, which is pi on 2. And z to the power of 4 is obviously that squared again, which is going to be 4 cis of pi. So look at that, 3 marks. Now the thing is that what is the average student going to do? Well, for starters, you can use your calculator if you like. You could use your calculator. You can go ahead and you can do it. And I'll show you right now. Okay, I'll show you right now what a waste of time this would be. Okay, so let's go 1 plus I. Got to press our pi button, and let's call that something. We've got to store that as a variable. So where is it? We've got to store as a variable. You can see how often I use this. So let's call that z. Okay, so then do z squared is 2i, and z to the power of 4 is minus 4. So you can see that is 4 cis of pi. 4 cis of pi is minus 4, okay? Z squared is, so 2 cis of pi on 2 is 2i, and of course 1 plus I, we know where 1 plus I is. So yeah, you could have done it, but what would have been faster? That's the question. Well, if knowledge is at your fingertips, you wouldn't be wasting your time in your calculator. But you can do it. I've just shown you how to do it. Okay, so it's just asking us simply to mark them out. 1 plus I, and there you go. Let's call it there. That's fine. Let's call that Z. And then Z squared is 2I, and isn't that the easiest marks you'll get? 4 cis of pi is the same as 4 minus 4i. So there you go. There's Z to the power of 4. Done. And look, if you're on the game, you could do that in 2 minutes, no problem. No problem whatsoever. Now, I'm going to get you to have a little bit of a read of this. There's nothing wrong with this question. So once again, it's an exam 2 question. They're lengthier. Because you can have your calculator, you can do all sorts of things. But at the end of the day, this is a show that question. I want you to try this question, please. There's nothing wrong with it. You just have to have a good look at it. It's the latter parts of this question which actually can be really quite tricky. Okay, so with this question, let's just we've been given so we've been given Z1. We need to show that the magnitude of Z1 is equal to 10 root 2. Just be careful, because in exam 2, sometimes these show that questions will take you longer. But let's see if we can do it. So U plus W. Let's do U plus W, and that's equal to 7 plus I. And then let's do U bar. U bar is equal to 6 plus 2i. And let's do IW. IW is equal to 3i squared is minus 3 plus I. So therefore, we can say that Z1 is equal to, we've got 7 plus I times 6 plus 2I over minus 3 plus I. What a work for 1 mark, isn't it? You do get these in these exam too. So that's going to be equal to 7 times 6 is 42 plus 14I plus 6I. And then we've got, what's that, plus 2I squared, which is minus 2, over minus 3 plus I, which is going to be, that works out nice and easy. That's 40 plus 20I over minus 3 plus I. So now, of course, we want to multiply that. We've got to show that. So it's minus 3 minus I. We've got to multiply by the conjugate. You can't convert that to polar form, can you? So it would be a waste of time doing that. So this would be a Cartesian one. So we've got minus 120 minus 40i minus 60i minus 20i squared, which is plus 20. And that's going to be minus 3 times minus 3, which is 9. 9 minus I squared, which is plus 1, which is 10. Okay, so we've got minus 100. So we've got minus 100. Minus 100 we've got minus 100i over 10, which is equal to minus 10 minus 10i. So therefore, the magnitude of Z1 is equal to the square root of 10 squared plus 10 squared, which is equal to the square root of 200, which is equal to 10 root 2 as required. A lot of work for 1 mark. But you probably need, just remember, you've done all of this. Whenever you're asked to show something, it's probably because you need to use it later. Okay, so just remember that. And it might not be part B. Okay, we're looking at part B now, and it's saying the complex number can be expressed as this. Find all of the distinct roots. Now, the distinct roots of z cubed is equal to z1. So, in other words, z cubed is equal to z1, which is 200 to the power of a half, cis of minus 3 pi on 4. Now, what I'm going to do is, what we're going to do is when we're going to go to z, we're going to actually apply that 200 to the power of a half. Now I'm going to change it because we're going to have multiple solutions around the complex plane. Minus 3 pi on 4 plus 2k pi. But when we do that in square brackets, and we do that, if we're finding the cube roots, then we're going to do that to the power of a third. So as you can see there, we're going to have some solutions, 3 solutions here. We've got 200, a half times a third is 1/6. And look at that, it's cis. We're going to have, now when we're applying de Moivre's theorem here, it's going to be minus 3 pi on 12, which is minus pi, minus 3 pi on 12, minus pi on 4. It's plus 2k pi over 3, such that k is an element of integers. Okay, so k can be anything. Now remember that the argument of z must be between negative pi and pi, inclusive of pi. Okay, which is on your formula sheet. So now what we're going to do is we're going to find our 3 solutions. So therefore we can say when k is equal to 0, k is equal to 1, and of course k is equal to negative 1 will be our 3 solutions which fit inside that. So therefore, give your answers in the form. They will be in that form. Yes, they will. So therefore, z, now it says give your answers, find the distinct roots of z cubed is equal to z1. Therefore, z1, so therefore z is equal to, when k equals 0, that's 200 to the power of 1/6, cis of minus pi on 4. There you go, there's one solution. When k is 1, we're looking at 2 pi on, 2 pi on 3. You can use a calculator for this, minus pi on 4, but I won't use a calculator. What are we looking at? We've got multiply that by 4. That's 8 pi on 12 minus 3 pi on 12. So that's going to be 5 pi on 12. 200 to the power of 1/6, cis of 5 pi on 12, like so. Didn't need a calculator, but they tend to ask these questions, harder questions, when you can use a calculator. So, and finally, it's 200 to the power of 6. We're looking at minus pi on 4, and then this time we're minusing 2 pi on 3, which is the same as minus. What did I do there? I did minus. That's minus. Yeah, no, okay, that's right. That's fine. Minus, yeah, that's fine. Okay, so we're looking at minus 3 pi on 12 and then we're looking at minus 8 pi on 12. So that's going to be cis of minus 11 pi on 12. Ask yourself the question, when we find a cube root, we're going to have 1, 2, 3 solutions. And as you can see, all of these 3 solutions are inside that range. And are they in this form? Yes, they are. A being 200 and 1 over n, n being 6. We don't have to state what that is anyway. Now, here it goes. Look, those 2 questions, not a problem, okay? 4 marks shouldn't be a problem, okay? But it'll be interesting to see how students go in those. So I want you to have a bit of a read of this question here. Now, think about it. What have we just done in part 1? We've done a show that question. And now that they're saying, let the argument of u be given by the, so let the argument of u, arg-u, is equal to negative alpha. By expressing IW in polar form in terms of alpha, show that this. Now, a lot of students just look at this and they just say, I do not have the slightest of clue how to do this. And we're sort of going to finish on this question for this video, because there's 3 plus 3 marks, which is 6 marks. And these marks were one of the hardest marks ever on an exam too, as far as students just didn't get them. So I'm going to pause it. I'm going to get you to think about it. Of course, you've got your exam booklets. So this was from 2010 exam 2. So you can take a look and give it a go in your exam booklet. I'm going to pause the video now, okay, and get you to have a go at it. And I don't care how long it takes you, but I just want you to say, imagine if you saw this in the exam under exam conditions. Can you do it? A lot of students couldn't. So pause the video now, give it a go, take as long as you need, take 15, 20 minutes. The main thing is I want you to really think about why you were asked to show that, and this really does require a deep level of understanding. Okay, so here's one I prepared earlier, and that is that in part, so we've been told that arg-u is equal to minus alpha. Now, if I can just draw, if I've got arg-u, so let's just say arg-u is minus alpha, right? Okay, so that angle in there is minus alpha. Then argument of u bar, okay, is going to be, so this is, let's call this u, this is going to be u bar, like so. Okay, so that's going to be alpha. Now, from before, from part A, IW is minus 3 plus I, and then the argument of IW is, in this case, we've got, what we've got is we've got minus alpha plus W. Why is that? Why is that the case though? Is because if I multiply W by I, then think about what that is. That's the same as W times cis of pi on 2. Okay? Now, cis of pi on 2 is a rotation of if I get, let's just say if W was here, okay, if W was here, then of course we have a rotation around like so, 90 degrees, 180 degrees. So that's where that plus pi comes from. Now, from before, we've got 2 root 10 cis of alpha, and IW is root 10 cis of pi minus alpha. So now using the things from part A, we've then got we've got U bar, and we've got IW like so. Okay, and then of course we're subtracting this angle pi minus alpha. We're subtracting minus alpha, which gives us 2 alpha minus pi. Now, not many students got that at all. Now, in actual fact, that question was done really poorly. Let's sort of see how students went on that one. So let me just pause. Okay, so as you can see, look at that, an average of 0.8. It was a show that question, which means that we were actually given the answer and we had to show that. So you can see there that that as I was saying, if you can understand from looking at it on an argan diagram, if I have u here with minus alpha and alpha being u bar, okay, the conjugate being of course, the same magnitude, just of course looking at it from a, sort of a reflection in that in the real plane, and then IW being a being we're multiplying W, whatever W was, I can't remember, and we're actually looking at that and multiplying it across and rotating it 180 degrees. Okay, so a significant number of students did not attempt this question because they just didn't know where to go. So these are the ones that you really need to follow. And have a look at this one. All right, I want you to try and have a go. Look at this one, even part D. This was the separator. This was the one that the students, 82% of students got 0 for the last one. Now, just quickly, if I just quickly show you that question, all right, you can pause the video now. All right, so I'll get you to pause it and have a look at that question and have a go at it. So, where are we at? Yeah, so with the last question, it says here, use the relation given in part A to find arg of u plus w. Well, arg of u plus w, you had to use the previous information. So arg of u plus w, well, first of all, we sort of said that Z1, if you're adding the arguments, okay, we know what the argument of Z1 is, and then we know that the argument of of alpha was this thing here, okay? So which we've been asked to show, which is 2 alpha. So the argument was 2 alpha minus pi. So we simply just had to rearrange that and use the previous information. But because most people gave up on part C, they couldn't then proceed with part D. So you can see there that that was easy enough. You've been asked to show that, and then you just simply had to rearrange. And in actual fact, it wasn't that bad a question had you have attempted part D. And as you can see, there, that most students simply gave up on that question or run out of time. In actual fact, question 5, it was the last question on the exam. And you see that really a very common occurrence is that towards the end of the exam, students simply run out of time. And even if they can do it, the question, they don't even have time to think about it. Now, that's the sort of question where if you can do your multiple choice exam questions, if you can save yourself time, you will save yourself a lot of time if you do things in a certain manner without having to resort to your calculator all the time. You have knowledge at your fingertips. And and finally, yes, that is a very tough question. So what I'm saying is, yes, complex numbers for the most part is an easy topic, but you can get some real tricky doozy questions in the exam too, particularly the extended response. Some of the early ones were easy, as you could see. Okay, even that students should I think that should be more 70% of students getting that. Okay, because for starters, you could actually solve that in your calculator using CSolve as well. And to at least get some answer marks, maybe more on the method marks. And of course, so the first part was easy, various methods accepted. So we're looking at 4 marks, but then there was the last 6 marks of that exam. 6 marks out of 80, and that was the difference between getting between getting maybe an A and an A plus, or a B plus and an A. But as you can see, not many students did that one. And in actual fact, that is probably the hardest the complex numbers question that I've seen on the exams. Okay, there are more questions to go through, so I will do that in part 2 of complex numbers exam questions. I'm going to stop this video here. I hope that you've learned something. Just remember that you've got to be very careful, and convert to polar form is a really important thing. And also understanding and drawing things on an Argand diagram like we've got here. This is the sort of understanding you need to do really well in complex numbers. I hope you've enjoyed. Thank you.